Hey Gemini, can you hear me?
I can hear you just fine. Is there anything I can help you with regarding the text on your screen?
Yes, I am wondering if you can help me with this physics problem for my mechanical engineering course. Now, I haven't taken physics in a lot of years, since high school, and so I'm wondering if you can help me out with this. Don't tell me the answer, but just help me figure this out. First, can you read the problem for me so I understand that you understand the problem?
Absolutely. Here's the problem. A water jet flows vertically upward at a speed v from a nozzle with a diameter d. At a distance L above the nozzle, the jet strikes a hemispherical bowl, where it is deflected vertically downward, as shown in the figure at right. The bowl is held steady and stationary by the jet. Determine the weight of the bowl in terms of known parameters. Assume inviscid flow in the jet, gravity directed vertically downward, and assume that the weight of the fluid contained within the bowl is negligible. Do you want to break down the problem-solving process step by step?
Yeah, I guess so. I'm just reading this along with you right now for the first time. So, the jet strikes the hemispherical bowl where it is deflected downward, shown in the figure below, is held steady and stationary where the jet determined the weight of the bowl in terms of known parameters. So when it says determine the weight of the bowl in terms of known parameters, I guess that means just in terms of other variables, not necessarily a numerical weight.
You've got it. Known parameters in this case refers to the variables given in the problem, not a numerical value. So you'll be expressing the weight of the bowl using 5, d, L, and any other relevant constants. Ready to start outlining the solution?
Yes. I have no idea where to start, so if you can just kind of walk me through this, keeping in mind not to tell me the answer exactly, but I have taken I do remember some physics concepts from my high school, like gravity and force equals mass times acceleration, things like that, but nothing too crazy.
Okay, let's start with the basics. The problem asks for the weight of the bowl, which is a force. Do you remember any physics concepts that relate force to the motion of an object, like the water jet in this case?
Yeah, so I'm going to write down here. So we know we're looking for the force of weight, right? And I know it's equal to mass times acceleration, like I mentioned. Coincidentally, that's actually what it's asking for. So we're going to have to find the mass and acceleration. I guess acceleration is gravity because it says g right there. So now we just have to figure out how to find m. Is that a good place to start?
That's a great start. Since we're looking for the weight of the bowl, we can use the formula you mentioned, Fw equals ma. In this case, the acceleration is due to gravity, so A equals g. Now let's think about how we can find the mass of the water that's interacting with the bowl. Do you remember any formulas that relate mass to the properties of a fluid, like its density and volume?
Yeah, I remember that density equals, let me see, like the mass divided by volume.
Exactly. Density, ρ(H)O, equals mass m divided by volume v. Since we're trying to find mass, can we rearrange that to solve for m?
Yeah, so it equals rho times velocity.
Almost. It's density times volume. Now let's think about the water jet. Can you see? You're on the right track. Think about the shape of the water jet as it leaves the nozzle. It's cylindrical, right? So how would you calculate the volume of a cylinder of water hitting the bowl per unit of time? Remember, the water has a speed v, and the nozzle has a diameter d.
So it'd be a cylinder. We have L here, so we'd assume. Okay, so it says assume inviscid flow in the jet. What does inviscid mean?
Inviscid means we're ignoring the effects of viscosity, which is like internal friction within the fluid.
Oh,
so we're
that's right.
treating
Okay.
the water as an ideal fluid in this case.
Okay, so then gravity directly downward, the weight of the fluid contained within the bowl is negligible. Okay, so I guess I'll assume that this is a perfect cylinder, so that's pi r squared h and then that'll be the volume. And then is that a good place to start off with the volume?
You're right about the formula for the volume of a cylinder. To apply it here, we need to think about the rate at which the water is ejected from the nozzle. The area of the nozzle is pi r squared, which can also be written as pi d/2 squared. Then, to get the volume flow rate, volume per unit time, we multiply the area by the velocity of the water, v. This gives us the volume of water hitting the bowl per unit time. Does that make sense?
That's right, yeah, because I forgot about this part. The nozzle's diameter d. So yeah, so it'll just, the velocity of water passing through this surface area, this circle will be what exactly? Will be the rate of flow.
The rate of flow would be the area of the nozzle times the velocity of the water, right? So mathematically, that's pi is 2 squared times v. Do you want to write that down, and then we can look at the next step?
So that's this v naught is the. So this is what does this all equal here when we multiply this right here?
That's the volume flow rate. So to get the mass flow
Volume
rate,
flow
mass per
rate.
unit time,
Okay, so that's a thing. So I didn't know that. So volume flow rate, I'll just call it like that. How is that going to help us get the mass of the bowl, though?
good question. The mass flow rate tells us the mass of water hitting the bowl per unit time. To find the total force exerted by the water, and thus the weight of the bowl, we need to consider the change in momentum of the water as it hits the bowl and is deflected downwards.
Oh,
Do you
so
remember
wait, is
any
the bowl
equations?
just floating there on top of the water?
That's right. The bowl is stationary, so the force of the water hitting it upwards must be equal to the weight of the bowl pushing downwards, plus the force
okay.
of the water being...
Oh, got it. Okay, so the bowl is held steady and stationary by the jet of water that's coming up here. So it's just, okay, so the force that it's getting, that the water's hitting the bowl is the same as the mass or the weight of the bowl. Okay, so that will get us the, what is this again? Velocity flow rate?
Yes, and we can use that to find the force of the water on the bowl. Do you remember the formula that relates force to the change in momentum of a fluid? It's called the momentum equation.
The momentum equation is that mass times velocity equals mass times velocity of the first objects to the second objects.
That's part of it. The momentum equation for a fluid is a little different. It states that the force exerted by the fluid is equal to the mass flow rate times the change in velocity of the fluid. In this case, the water's velocity changes from v upwards to v downwards. So the force exerted by the water on the bowl...
Hey Gemini, sorry we got disconnected. Do you remember where we were in this conversation? In the previous conversation?
Yeah. Okay, I remember we were discussing the water jet problem. We were about to figure out the weight of the bowl, right? Did you want to keep working on that? Or did you have something else in mind?
Exactly, yeah. So you were, what were you telling me about this right here?
Okay, so we're trying to figure out the weight of the bowl using the water jet's momentum, right? We've got the equation for momentum in there. How do you think we should apply that to the water jet hitting the bowl?
Well, this is the normal momentum equation. However, you were telling me that there was like a fluid dynamics. I don't know. I haven't taken any fluid dynamics courses or anything. So you were telling me that there is like a specific fluid dynamics momentum equation that relates the mass of something with the fluid, the velocity, fluid rate, or something like that.
You're right, we need to use the momentum equation for fluids here. It involves the density of the fluid, the area of the nozzle, and the change in the fluid's velocity. We can use that to find the force exerted by the water on the bowl, and then use that force to find the weight of the bowl. Does that make sense?
Okay, so what's that fluid momentum equation, if it's not this standard one?
The equation you're looking for is Force equals density times area times velocity squared. This relates the force exerted by the fluid to its density, the area it acts over, and its speed. Does that make sense?
So you said force equals density times area times the velocity squared?
Yep, that's the one. So how do you think we can use that to find the weight of the bowl?
All right, so that means that the area is this little nozzle here, which is d sub 0. So pi d sub 0, that's the diameter. So we want pi r squared, actually, so this is wrong here. So the force is equal to the density of water. I guess this is water, yeah, water jet. So I think that's like a standard thing that's known. The area is going to be pi r squared, so that's pi, and then r is going to be the diameter divided by 2 squared. And,
You're on the right.
and then and then the velocity is just this v naught, I guess, because it's coming out right there, v naught. So v naught squared. So that's, so where am I at so far?
You're doing great. So now that we have the force from the water jet, how can we use that to find the weight of the bowl? Remember, the bowl is stationary, so the forces must be balanced.
So whatever this comes out to, or I guess this is the answer then, because this is the force of the jet coming out of the nozzle, and that's equal to the bowl. But it seems like there should be, I don't know if these are distractors, like velocity 1, like as it slows down after this length, then and then this v2 here on the sides. I imagine the force that's coming out of this nozzle is not equal to the force that the water is hitting the bowl at if it's at a distance L. So doesn't that force like decrease by some degree after it traverses this distance L?
You're right, the force of the jet decreases as it travels upwards due to gravity. To find the force when it hits the bowl, we need to consider the change in velocity over that distance L. We can use the formula for velocity under constant acceleration to find the new velocity, and then plug that into our force equation. Do you want to try working through that calculation?
Yeah, so I guess is it just like the normal acceleration equals velocity 2 minus velocity 1 over a specific time, but I don't really know. So, but if acceleration is gravity, which is 9.8 meters per second squared, then velocity 1 is v naught, so 9.8 meters per second squared equals the velocity 1 minus velocity naught over the time it traverses, which is here, velocity 1 minus velocity naught. But do I put that into here, or do I just put the velocity here as velocity 1 instead of velocity naught, and then we just assume that the area here, well, no, because that's not the same.
Got it. So you'll use v1 squared equals v0 squared minus 2 times gravity times L to find v1. Then, plug v1 into the force equation, F equals density times area times velocity squared, to find the force exerted by the water on the bowl. That force will be equal to the weight of the bowl.
Wait, can you repeat that again? So am I just, I feel like I can't, so if this v naught here is this part right here is what?
No worries. So the v in your equation is the initial velocity of the water jet as it leaves the nozzle. Does that make sense?
Yeah, so this would be the force of the water coming out of the nozzle. But how do I incorporate the deceleration of this nozzle into this section here? Because it's just the new velocity should I just put velocity 1 here, since velocity 1 is the velocity of the water coming out of the nozzle as it hits the bowl, and then that'll solve our problems, assuming that the area is still, that diameter divided by 2, even though in reality it might be kind of spraying out a little bit. But then we wouldn't include this L, in which case the L would be a distractor. So is that a solution? Can I just put V1 here, or do I have to incorporate this length here and consider the deceleration of the water flow coming up around here?
You're right, we need to consider the deceleration. The water slows down due to gravity as it travels upwards. We can calculate the water's velocity, v1, when it hits the bowl using the formula v1 equals square root v0 to the power of 22gl. Then, we'll plug that v1 value into the force equation to find the force exerted on the bowl, which is equal to its weight.
Okay, so we don't use this normal, we don't use this equation.
That's right, we don't need that equation. We can find v1 using the formula I just gave you, then plug v1 into the force equation to solve the problem.
So what exactly, so it's what's the equation? Square root of what?
It's the square root of v0 squared minus 2 times gravity times L. Ready to plug in the values and solve for v1?
So does it look like this?
Yep, that's it. Now we just need to plug in the values and calculate v1. What do you get when you do that?
There are no numerical values, so I guess we just leave it at that.
Exactly. So we'll leave v1 as square root, v squared 2gl. Now let's plug that into the force equation to solve for the weight of the bowl.
Wait, but this, where'd you get this equation?
We got it from the formula for final velocity squared, which is initial velocity squared plus 2 times acceleration times displacement. In this case, the acceleration is due to gravity.
Can you do that slower so I can write it down?
Sure thing. The formula is final velocity squared equals initial velocity squared plus 2 times acceleration times displacement.
Okay, yeah, I think I remember this formula. So does that mean then, so then we got the final, so squared, so then initial velocity squared minus, so why are we subtracting here instead of adding? Because we're looking at the final velocity, which is v1. Shouldn't it be v initial velocity, the square root of initial velocity squared plus 2 times acceleration times distance?
You're right, the general formula does have a plus sign. However, in this specific problem, gravity is slowing the water down as it goes up. That's why we use a minus sign here. It shows the water losing speed as it rises.
Oh, okay, that makes sense because this is assuming positive acceleration, so this is like a negative 9.8 meters per second. Got it. Okay, so then we just plug that into here, and then square all of this, which is going to cancel out the square root. So then it's just this initial velocity squared minus 2 gravity length for this part here, and then that's the answer. So the force of weight of the bowl is equal to the density of water times pi, and then diameter squared over 4, I guess we can just say. So the diameter squared over 4, which is basically, I can just put this all up in the numerator, so I'll clean that up maybe after. And then this velocity initial squared minus 2gl is really the square root, so I'll just work through this. Hold on one second. Velocity initial squared minus 2gl all squared, and then if we clean this up, then the force of weight will be rho pi diameter squared. Maybe we can just put that all, we'll put everything over 4 at the end. These two cancel out here. we're left with parenthesis V initial squared minus 2 gravity length it traverses, all divided by 4. Does that look like the right answer then? Or am I missing anything, or am I incorrect in any part? Hello, Gemini. Hello, Gemini.
Hi there. I see you've written out the formula, substituting V1. How can I help you with it?
Does this look like the right answer?
You're super close. Just a small correction. The density of water is represented by the Greek letter rho, which looks like a P. It's written like this, rho. So the final answer should be, force of the water equals density times pi times d0 squared over 4, all multiplied by v0 squared minus 2gl.
All right, cool. Thank you so much.
You're very welcome. I'm glad we could work through it.